comma, we have a complement, which is all the elements X, such as X is not an element of A. Right there. So that is similar to the operation. What is the operation A complement in logic, in the logic world? What could it be?
A naught.
A not, well, not A, not A. Okay with that right there, or not Q. The not Q is just like the A complement. And you can think with the diagram, with the set diagram, a Venn diagram. With the Venn diagram, I could have the set A right there, and not A. A complement is everything that is outside. Right there. Everything that is outside is a complement. There. A union A complement, they give you the universe. So I will define union in a minute. But A union A complement, that will be the entire universe right there. So mu stands for the universe that you have defined. That's it. The universe that you have previously defined right there. So, okay, there. Well, that's it. Let's talk about union. That's one operation. A given sets A and B, comma, we have A union B. All the elements X in the universe such that X is in A or X is in B. So sets tend to get larger under the operation union. It's an OR. The union is the OR for logic right there. So sets will get larger unless one set is inside the other one right there. They will not get larger in that situation. If one set is a subset of the other set. So I'll go over that definition in 5 minutes. Subset. There we have the union, but then we also have the intersection where the sets will get smaller. It's all the elements X in the universe, such as X, it's in A, and X is in B. So the intersection is the AND in the logic world. So here is the OR, and here is the AND right there. And sets will get smaller when you are taking intersections. They're more likely to get smaller right there because you're asking for more requirements to be met right there. So, okay, you have those two. The other, it's A is a subset of B. Means if and only if, means if X it's an element of A comma, then X, it's an element of B. Right there. So those are popular notation right there. Now, it could get larger. Right there, you could have A1 union A2 union A3 all the way to union AN right there. So the union of n sets. Well, we have notation for that. It's a big union. I goes from 1 to n of AI. And that will be the union of n sets right there. We have notation for the intersection of n sets. A1 intersection A2. Intersection A3 all the way to AN. And the notation for that will be a big intersection like that. AI. Let me circle those two. There. And the other one. Right there. So once we have that, we can actually, let me see what else. Potentially we have a power set. So given a set A, X, given a set X, comma, we want all subsets of X. All subsets of X. And then we call that power X or PX like that. And that will be the power set. An example, X, it's ABC. So then power X is all the singletons, A, B, C. And we're reviewing a little bit because we have seen, we've done some homework like this. ABC, AB, BC, AC, X itself, the set itself, ABC, X is a subset of itself right there. All subsets. And ultimately the empty set. And today we will prove that the empty set is a subset of every set. Right there. So let me put a fence. Many times we need to prove set equality. We need to prove set equality. I need to prove that some expression, some set right here, let me make it like this, some set, it's equal to another set. Right there. I'm making those pictures like that, but set equality. To be able to prove set equality, that's if and only if. Right there. So the proof needs to go like this. You need to show that the set with the stripes is a subset of the set with the polka dot. That's the first part of the proof. And the second part of the proof is conversely. So then you say conversely. Right there. Then you need to show that set polka dot is a subset of set stripe. Right there. Can you see two parts right there? Two parts. Let me give you more details about the structure of the proof. That's what I'm talking right here about the structure of the proof for set equality. The way to prove many of these proofs is like this. Let me say it again. Meaning, let me repeat that. Use the same example. Show that the set stripe is equal to the set polka dot. Right there. Well, we know what we need to do. We need to show, well, the proof will say, okay, proof. Show that stripe is a subset of polka dot. Well, the structure of the proof, you're going to take an arbitrary element in said stripe. Take an element from said stripe and do some computations with that. Manipulate, write sentence to show X is in the set polka dot. Right there. That's the standard proof. Pick an arbitrary element in the set stripe and show that is in the set polka dot. And that will be half of the proof. Then you need to say conversely. To show the other way. To show that the set polka dot is a subset of the set stripe. Pick an arbitrary element. Call it Y or also call it X. Call it X. Pick element X in polka dot. Use definitions. Use your ingenuity. You use complete sentences to ultimately show that that element X is in the other set right there. Okay, with that, so what would I use? I use the definitions of because that will have some structure, some algebraic structure. So I would use definitions, some computation, and then ultimately show that. So here is manipulate, comma, write sentence, use definitions. Complete sentences. To ultimately show, to show X has to be in stripe. So if you do both, that's it. Then you write a conclusion. Hence, thus, the two sets are equal. Right there. We're not using Venn diagrams to show that they are equal. We're using sentences to show that they're equal. But in a lower level class, like college math, they will use Venn diagrams and they will shade and show that they must be the same. Let me give you an example. Let me see. I wrote an example right here. They were proving this in the other discrete math, in the discrete math at ACC that they have for the 4-year degree. So the computer science. So I saw that in the I walked through the classroom, and this was in the blackboard of the other class last semester. The computer science for the 4-year degree. It said this. It said, show. So example. That's what I saw. Example 1. Because they were manipulating this result in a computer program. They needed this for a computer program. So here it said, example 1, show that for every 2 sets, for all A and B sets, A minus B, it's equal to A intersection B complement, right there. Can you see? I need to show that those 2 sets are equal, right there. I never gave you the definition of A minus B, so let me give you the definition right away. Right there. A minus B is defined to be all the x's such that x is in A and x is not in B. Right there. So that's it. I should have put that definition way above. So perfect. That is the complement of B in A. That's what it's called, A minus B. The complement of B in A. Right there. Happiness. Perfect. So let's go and prove it. Right there. So prove. Let A and B be sets. So that's my first complete sentence. Now, pick an element. Pick an arbitrary element right there. So let, here comes, let, oh, let me use the let from first grade, the L. Let X be an element Oh, let me write this. What do we want to show first? That would be nice to show, write this sentence. To show that A minus B, the complement of B in A, it's a subset of A intersection B complement, period. That's what we want to show. Okay, pick an element. So I will say let X be an element of A minus B, or pick. Oh, yeah, let little x be an element of A minus B. Perfect. We have that. Then, of course, I will go through the definition. That's what I'm going to use next. There is the definition. So I'm going to write that definition as a sentence. Right there, because that's what it is. A minus B. So then I will say, so, right there. Or then, so X is an element of A. And X is not an element of B. Right there. Happiness with that. Perfect, perfect. So, the next sentence. Since X is not an element of B, my voice is changing out of emotions right there. It gotta be that is in the complement. X is not an element of B. So X is in the complement of B. So X is in B complement. Happiness with that. So, therefore, or see that again, I'm being repetitive. X is in A and X is in B complement. Thus, X is in A intersection B complement right there. Can you see what we did? We picked an arbitrary element that it was in X minus A, and I ran through the definitions with complete sentences to show that it was on the other set right there. To show that it had to be in A intersection B complement. So then I can say, hence, A minus B is a subset of A intersection B complement, period, right there. So sometimes we get stuck in these proofs, so they're not trivial, but so far I've used the definition in complete sentences. Let's take a look at the other direction. The other direction is to show the converse. So I will write conversely. Conversely, to show A intersection B complement is a subset of A minus B. The set difference right there. The complement of B in A. Perfect. So, okay, same thing. Let X pick an element. I could say pick. Oh, let me say pick this time. Pick X in A intersection B complement. Right there. And then I will run through the definition. Oh, let me pick Y. Let me pick Y. Susanna, I've seen Susanna's proofs that she picks Y. Doesn't matter. You can also use X. You can use X on both. Right there. But let's pick Y because Susanna sometimes likes to do that. So pick Y, an arbitrary element Y in A intersection B complement. And run through the definitions. Just verbalize the definition. So then you'll say, well, then Y, it's an element of A, and Y, it's an element of B complement. Can you see? I'm saying what it just says in symbols right there. Next, well, I'm gonna concentrate on B complement. I'm gonna say since Y is in B complement, it must be the case that Y is not an element of B right there. because it's in B complement. It's outside of B. Right there. And then I have it. Y is in A and Y is not in B. And that's what I will say next. Now, I'm going to say this. Recall that Y is in A because maybe so recall that Y is in A and Y is not in B. So, comma, by definition, or we can see, recall that Y is in A and Y is not in B. So we can see that Y is in A minus B. Right there. So that's it. So thus, A intersection B complement is a subset of A minus B. Right there. So to conclude, A minus B equals A intersection B complement, period, and the little box. Right there. Happiness with that. Right there. So they feel a little bit different, but those are the most popular proofs in section 6.2. Let me take a look at another example. Right there. Perfect. This one. Right there. Let me put the pen right here for like 3 Mississippis. And I'll do now one example that is in the textbook in section 6.2, which is theorem 6.2.3. Right there. Let me see. So page 400. So theorem 6.2.3, page 400. Section 6.2. Right there. So here it comes. Well, the irony is that the example that we did before is more important than the theorem that I'm writing right now. Okay, with that, so the one above, the one that I did before should have been a theorem also. Okay, with that, so don't look down on this example as if it's not important. This one that was on the blackboard on the discrete math class for the 4-year degree at ACC in internet security, right there. It should have. This is a theorem. This is important too. So perfect. So let me give you this one, the one that is on page 400. For all sets A and B, A and B, comma, if A is a subset of B, then A intersection B, it's equal to A. Right there. Okay with that. Okay, usually sets get smaller with intersection, but A is a subset of B. Right there. Oh, okay, there. so A intersection B is A, right there. We can make a Venn diagram, but that's not the proof. There we have the set B. There we have the set A, right there. And we can see the A intersection B is A with the Venn diagram. Right there. But that's not the proof. So let me put a little fence right there. That's just a picture. Happiness right there. Perfect. So that's it. We can start this proof right there. So okay, proof. Let A and B be sets. There. Then we are going to assume the hypothesis. Assume A is a subset of B. Right there. Perfect. Assume A is a subset of B. Period. So then it will be set equality. This will be set equality right there. Show to show the A intersection B is a subset of A. That's the first part. I'm not writing the proof like Susana in the textbook. I'm writing the proof different. So let me emphasize that. I'm not going to write a proof exactly like the author of the textbook. They will, then you can read it yourself. I will be wasting your time right there. So I'll write it with my own style. Okay with that? Okay. If not, we don't gain anything by me just reading the book to you. Right there. So I'll do it with my own style, different than Susana. So to show A intersection B is a subset of A. So that's it. Let X be an element of A intersection B, comma. So, by definition, X is an element of A, and X is an element of B. Thus, X is an element of A as desired. Right there. Can you see that was easy, but I could have written that it's obvious that A intersection B needs to be a subset of A right there. But of course, if you say obvious, no, I mean, let's write some sentences and show that that's the case. Happiness. Perfect. Now the conversely. To show that A is a subset of A intersection B. Right there. Perfect. To show that A is a subset of A intersection B. So let X be any element in A. Pick X. Any element. Oh, pick any element X in A. Pick any element X in A. Right there. We must show we must show that X is in A intersection B. Right there. Perfect. Look at the hypothesis. By hypothesis, A is a subset of B. Right there, comma. So, X is an element of B. Right there. See that? X is in A. And X is in B. Thus, X is in A intersection B as desired. Right there, period. To conclude, we got it. We did the two pieces. To conclude, A intersection B equals A. Right there. Okay, let me pick another. Let me see. Perfect. Right here. Put a little box. Right there. Let me see. There. I'm looking for more examples. Okay, let's take a look at this one. Show. Right there. That for all sets, A and B, comma, A intersection B complement, it's equal to A complement union B complement. Right there. What should we call this theorem?
Is this De Morgan's law?
Definitely. Yes. Thumbs up. Thank you, Ansley. Yeah. This is De Morgan's. This is one version of De Morgan's. Then we have the other one. So this looks like when our friendship just started. P and Q not equivalent to not P or not Q. Yes, De Morgan's. So I'll put it right here. Right there. So let's try to prove De Morgan's right there. Perfect. So proof. Right there. So let A and B be sets. Right there. So perfect. To show A intersection B complement is a subset of A A complement union B complement, right there. So we'll pick an element. We'll pick an element on the left-hand side and show that it's on the other one. So let X be any element in A intersection B complement, right there. Happiness with that? Perfect. So that means that X is not an element of A, it's not an element of A intersection B. Happiness. Okay, what could I say next? Case one. X is not in the intersection. So case one. Let X be in A and X is not in B. Okay, with that, I have to have some cases right there. X is not in the intersection. Let me make a little picture right here. So here it gets a little bit more complicated. X is not in the overlap of A and B. Let me make the picture right there. There is A, there is B, and X is not in the green part. So X could be here, but not in B. X could be here, and X could be there. Can you see all the places where X could be? So three cases. Case one, case two, and case three. Right there. Perfect. So that's it. So let X be in A, and X is not in B. So since X is not in B, it must be the case that X is in B complement. Hence, X is in A complement union B complement. Right there. Happiness. If you're in Texas, you are in Texas Union, Louisiana. Okay with that? Okay, perfect, perfect. Okay, case number two is very similar. Case two. Right there. Let X not be in A and X is in B. Right there. So because X is not in A. Then X, it's in A complement. Hence, X, it's in A complement union B complement. Right there. Perfect. There. And then we have one more. Assume case 3. Right there. Case 3. X, let X not be in A, and X is not in B. Right there. X is not in A, and X is not in B. So X is in A complement. And I need only one of them. X in complement, and it must be the case that X is in A complement union B complement. Right there. So that's it. Those are the 3 cases that I grabbed from the picture, because X was in A intersection B complement. X was in A intersection B complement. So it was not in the intersection. So not here. Let me get the picture. X was not here. So it could be in 3 spots right there. Somebody could potentially read my proof and think that case 3 is redundant, but I don't think it is right there. I like it to be in those 3 different places right there. A, B, or outside A and B. Happiness? Perfect. Next, conversely, there, conversely, we want to show the opposite right there. Show that, conversely, to show that, and then the other containment. The other containment is the A complement union B complement is a subset of A intersection B complement. Right there. Happiness? Perfect. Pick an element. Let X be an element of A complement union B complement. So X, it's an element. Oh, 2 cases. X is an element of A complement union B complement. So case 1, X could be in the complement of A. And case 2, X could be in the complement of B. Right there. So 2 cases. Case 1. Right there. X is in A complement. Comma. So X is not an element of A. Right there. What could I say next?
Could you say that X does not satisfy the definition of the intersection between A and B?
Okay, yeah, perfect. Yeah. Since X is not in A, X is not in A intersection B. Right, perfect. So X is not in A. Thus, I'll say it with words. So X not in A implies X not in A intersection B. Perfect. Right there. Yeah. If you are not in Texas, right there, you are not in the intersection of Texas and some other. Yeah. Well, let me look at a country that have intersect. Yeah. Yeah, perfect. Yes. You are not in A, so you are not going to be in A intersection anything right there. Perfect. Thus, X is in A intersection B complement right there. Perfect. Case number 1. The other case is going to be very similar. Case number 2. It's a pure formality right there. X is in B complement right there. So by definition, X is not in B right there. Hence, X is not in A intersection B. So X is in A intersection B complement. Right there. So let me see. There. That's it. We've shown both. So to conclude, A intersection B complement, it's equal to A complement union B complement as desired. Right there. And the little box. Perfect. Right there. What else on the examples? Let me see. There. Perfect. This one. Theorem. Six 6.2.3. 6.2.4. Right there. A set with no elements. A set with no elements is a subset of every set. Right there. That one. So here it comes. If E is a set with no elements, comma, then E is a subset of A for all sets A. Right there. Perfect. A proof by contradiction. There. Assume E it's a set with no elements. And I'm putting the big symbol for and right there because we're writing the negation of that statement. So assume E is a set with no elements and E is not a subset of A for some A, for some set A. Can you see? I wrote the negation, existential. Some set A, for some, there exists a set A, such as E is there, and E is not a subset of A, right there. So, perfect. By definition, here, let me be repetitive. Since E is not a subset of A, comma, then by definition, there is an element X in E such that X is not in A, right there. That's the definition of not being a subset, right there. So let me see. I gave you the definition of a subset way up here when the class started, right there. Let me see. There, subset here. I gave you the definition of a subset. Let me give you the definition of not being a subset. So A is not a subset of B means right there that there exists X in A. There exists an element X in A such that X is not in B, right there. Because remember, if A is a subset of B, every element in A is in B, right there. So perfect. So then let me go and use it right here. Perfect, right there. But that's a contradiction. Vacuous truth. That's the contradiction right there. E has no elements. E has no elements right there. I will say, see that we have a contradiction. I can never satisfy that line right there. We have a contradiction because E is empty, comma, it has no elements. Hence, E is a subset of A for all sets A, right there, as desired. There, for all sets A, as desired. And then the little box right there. So then I can go all the way at the top when we started today, all the way at the top. Remember that we looked at the power set. Yes, the empty set is a subset of every set. Right there. Empty is a subset of every set. Right there. We just proved it. So the next thing that we have to do is prove that the empty set is unique. Right there. So that's show. Let me see all the way here. Show, another example, show that the empty set E is unique. We have one and only one empty set. Let me repeat that. So show that we have one and only one empty set. Perfect, right there. So how do we prove uniqueness? We assume we have two empty sets right there. So that's the technique that's the most popular technique to prove uniqueness. Right there. So let me put an analogy. How can we show that Camila has one boyfriend? Right there. Camila has one and only one boyfriend. The most popular way is contradiction. We assume that she has two boyfriends. One boyfriend is Marcelo, and the other boyfriend is Ludovic. And Ludovic, and we arrive to a contradiction. Marcelo is Ludovic. Okay, with that, they're one and the same. Happiness. Okay. I hope the analogy work and it's not a weird analogy right there, but that's what we do right there. So perfect. That's the most popular way to show uniqueness. So that's it. By contradiction, assume that we have two empty sets. So proof by contradiction. There. Assume E1 and E2. I need to put the pen really fast for 5 seconds. Assume E1 and E2 are empty sets. Right there. So I'm charging. So that's what we're going to do. Then, of course, by the previous result, E1 is a subset of E2 because E1 is empty right there. So let me see. I'll write it. Assume E1 and E2 are sets right there. Are sets. Assume what? Empty sets. Assume E1 and E2 are empty sets. And now you take one by one. Because E1 is empty, comma, then E1 is a subset of E2 because E1 is empty and the empty set is a subset of every set. Similarly, assume, because E2 is empty, It's an empty set. We have E2 being a subset of E1. So then they must be equal, and there is one and only one empty set. Thus, E1 equals E2. And we have one and only one. Empty set. And now we can use the symbol. Empty, right there. Is one and only one. Empty set. And we call it empty with that symbol right there. Happiness with that? I'll put the box as desired. And put the little box right there. There. Happiness. Perfect, perfect. So any questions, any questions? So this section could be slightly spicy. We can get stuck sometimes, but they're all proofs with sets. So super freedom,